Okay guys, let's look at question 38. Now, before I proceed, I would like to let you know that my writing is going to be really horrible. Writing on the screen with a pen is totally different than writing on a piece of paper. Okay, let's look at question 38. This diagram shows a section of a polylactic acid, PLA, a biodegradable and bioactive polyester derived from renewable resources such as cornstarch and sugarcane. And question A is asking you to draw a monomer required to produce PLA. Now they're asking you to draw monomer, not repeating units, monomer. So you're supposed to draw the actual molecule that was used to produce PLA. Now if you noticed, they've already mentioned in the question that it is a polyester. Okay, if it's a polyester, there's only two ways to make this polymer. Either you use two different monomers, monomer 1 with dicarboxylic acid groups, and another monomer with dihydroxyl groups. Okay, or you can also make polyester with one monomer but with both the functional group present. Okay, so let's see what kind of a monomer that was used to make this PLA. Okay, first things first, what you need to do is to cut at each of the ester bonds. Now where do you cut ester bonds? You're supposed to cut them here, 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 here. Okay, and if you notice, you can't see two distinctive patterns. You can only see a repeating similar molecule, a single molecule that is repeated. You can't see two different molecules. Okay, so I'm going to take this one here, somewhere in the middle. Don't take the end part. Okay, take the middle molecule so you can be really sure of the monomer. Okay, so I'm going to draw that. Okay, I'm going to draw that here. So it's C, double bond O, H, and CH3. Now remember, this is not complete. Like I said, you either have this type of monomers or this type of monomers. Now since you can see only a single monomer being repeated, it's clear that the polyester was made with a monomer that has both carboxylic and hydroxyl group present. So obviously this part here is going to be the carboxyl group because it has a carbonyl group here already. So just add your OH, and here all you have to do is add H, and that's your monomer. Okay, next question. Name two attractive forces exhibited between the chains of PLA that makes it suitable to be used as material in three-dimensional printing. Attractive forces between chains of PLA. Now, I think a lot of you all wrote hydrogen bonding because you looked at the monomer. Now, the monomer, yes, it has carboxylic group, and it also has a hydroxyl group, which clearly shows hydrogen bonding between the monomers. But what they're asking is between the chains of the polylactic acid. Now if you look at the chains of polylactic acid, no hydrogen bonding can be present between the chains of polylactic acid. Okay, the only interaction that can be formed is dipole-dipole interaction because there's carbonyl groups, and obviously dispersion forces because dispersion forces exist in all molecules. Okay, hydrogen bonding cannot be present. So it's dipole-dipole and dispersion. Alright, next question. Okay, in a polymerization process of manufacturing PLA, the monomer was charged to the reaction vessel at a high temperature and pressure. This is to ensure the highly endothermic condensation reaction is completed at a reasonably high rate. Draw and label a potential energy diagram that reflects the condensation reaction. asking you to draw energy potential diagram. And the reaction is endothermic, highly endothermic. So you're supposed to start with your reactants, okay, and then you have the bump, and you have this. Okay, please make sure you draw it neater than mine. Okay, the pen is very slippery on the screen. Okay, so here is your lactic acid, this is your polylactic acid, and this would be your activation energy, and this would be your delta H, energy absorbed. Now make sure all of this is at the same line. Okay, 3 marks for the curve, for the activation energy, and the labeling of delta H. Right, next, titration experiment. Okay, at the end of the polymerization, the wastewater produced from both washing process and the byproduct of condensation reaction was used to determine the percentage of conversion of the lactic acid monomer. Now, I noticed a lot of students could not understand the whole purpose of the titration. Now, what we are doing is we are going to try to convert all this lactic acid into polymer. But obviously, there's going to be some remnants that was not used in the polymerization. So the whole titration experiment is to identify how many percentage of this was converted into polymer. And how do you do that? By identifying how much remnants were available. Okay, the excess or the unused lactic acid monomers was titrated with sodium hydroxide. Okay, and then you'll have to subtract it from this to identify how much of this was converted to polymer. Okay, now first step, this amount was used in the polymerization and it produced 400 liters of wastewater. Now in this wastewater, there's going to be remnants or unused lactic acid monomers. Okay, so 20 ml of this wastewater was then diluted to 250 ml, the usual. Okay, and then 20 ml out of the diluted solution was then transferred to conical flasks and titrated with sodium hydroxide solution. Okay, and they asked you to complete the results table above. Now remember, there's no marks here, no mark allocation for the results table. Okay, so just fill in. You still need to fill in though to find out the titer values. Okay, and finally, to identify the average titer value, make sure you only use this because these are the 3 closest reading. Okay, doesn't matter how many readings were given, you're supposed to take only 3 closest reading to get your average titer value. Okay, now let's calculate the percentage of conversion. First step, okay, in order for you to identify what's happening, let's just draw what happens. Okay, to simplify whatever that was written in paragraph, let's just draw. Now what you have is 400 liters of wastewater, okay, which has lactic acid. Now the key point here is it has lactic acid. It's not the wastewater that you are calculating, you are calculating the lactic acid, and when you are calculating the number of moles, make sure you label them correctly. Okay, now out of this 400 liters of wastewater, 20 ml was taken out. So this 20 ml then is transferred into a 250 ml volumetric flask and diluted to 250 ml. And out of this diluted solution, 20 ml is taken out, poured into a conical flask and titrated with standardized sodium hydroxide solution. Of 0.104 molar concentration. Okay, let's start with the calculation. Now, first things first, you always start with the standardized solution because that's the only confirmed value that you have. So in order to find out the number of mole of sodium hydroxide solution standardized, you first have to find out the average titer value, which is the 3 closest reading that you took earlier. So you got a value of 16.25 mil. Okay, next, find the number of moles. Now make sure you write everything clearly. So here, convert your ml here to liters, so you'll get 0.01625 multiplied by 0.104, the concentration of the sodium hydroxide. You get 1.69 mole. Okay, next, once you have gotten your sodium hydroxide moles, you have to identify how many moles of lactic acid was reacted with the sodium hydroxide. How do you do that? Is your lactic acid a monoprotic, diprotic, triprotic acid? How do you identify that? You have to go back to your monomer. Okay, and as you can see, you only have one carboxyl group, and each carboxyl group donates 1 H. So obviously, lactic acid here is a monoprotic acid, so it's very easy. So basically, the number of mole of lactic acid reacted in the conical flask is the same as the number of mole of sodium hydroxide, which is 1.69 times 10 to the power negative 3 moles. Okay. Next, you have to go backwards. Okay, so you have identified the number of mole of lactic acid inside here. Now you have to go backwards and find out the number of mole of lactic acid in your volumetric flask. Okay. So the number of mole of lactic acid in 250 ml is this, divide by 0.02, which is 20 ml, multiplied by 0.25. Okay, so you will get 0.021125 moles. So this is the number of mole of lactic acid present in your volumetric flask. Now again, you have to go one more step back, which is the number of mole of lactic acid in this 20 ml undiluted wastewater. Okay, now remember, from this step to this step, all you did was dilution. So the number of mole of lactic acid in your volumetric flask is equal to the number of mole of undiluted 20 ml wastewater. So please write that down. Okay, this information is very important, because if not, the next step will be wrong. So the number of mole of lactic acid in 250 ml is the same as the number of mole of lactic acid in undiluted 20 ml wastewater. Okay, now one last step, identifying the number of mole of unreacted lactic acid in your 400 liters of wastewater. Okay, so all you have to do is the final number of mole that you got, which is this one here, divide by 20 ml and multiplied by 400 liters. Okay. Divide by 0.02, don't forget to convert it to liters please, times 400. And you will get 422.5 moles. Okay, now remember, this 422 2.5 moles are just moles of lactic acid that was unreacted. So you still have to find the original number of lactic acid present to find out the conversion rate. Okay, so you have to find out the original number of mole of lactic acid in 400 liters. And how do you find that? They've given you the mass in the question. Okay, so you just have to divide it by your molar mass. And how do you get the molar mass? Is from your monomer. So yeah, if your monomer was wrong, your molar mass would definitely be wrong. Okay, so based on the monomer that I just drew earlier, I would be getting about 90.078. Okay, so I will be having 11101.49 moles. Okay, so after that, very easy. You have your original, you have the unreacted number of moles. All you have to do is minus. Okay, so number of mole of lactic acid converted to polymer is 11101.49 minus 422.5. Get 10678.99 moles. Okay, and percentage of conversion would be, take the number of moles that was converted over the original amount, and you would get 96.2%. Okay. Okay, last two questions. This is generally the basic questions. List two reasons that sodium hydroxide cannot be a primary standard. So generally you can say the fact that it can't be obtained in a pure form, it cannot, it is hygroscopic. Don't forget, the spelling is hygroscopic, or it can also absorb moisture from air. Sorry, these two are the same thing, so I'm gonna write it together. From air, or you can say reacts with CO2 from air. Now, low molar mass is not accepted. Like in your marking scheme, low molar mass is not accepted for this question because low molar mass implies that it has such a low molar mass to the point that you can't weigh it in the lab and prepare a solution. But you know, you have prepared sodium hydroxide solution many times in lab, so the molar mass is not that bad. Okay, now if you were to compare it with sodium carbonate and then you mention it has a low molar mass relative to sodium carbonate, then it can be accepted. But again, that answer is not relevant to this question because here they're not asking you to compare it with sodium carbonate. They're just asking you why sodium hydroxide is not a good primary standard, full stop. Okay, so these are the usual explanation that can be accepted, which is hygroscopic, react with CO2 from air, or you can also say it can't be obtained in a pure form. Okay, next, last question. Okay, if this sodium hydroxide solution is prepared by dissolving a certain weighed amount of sodium hydroxide pellets in water, which is made up to the stated concentration, predict the effect of this standard solution. Now, most of the students who wrote this answer end up writing the titer value will be higher or lower, higher or lower. Now, there is only one answer, which is higher. Okay, how will it get higher? Now, if you have looked through the question earlier, the sodium hydroxide was standardized to this concentration. meaning it was titrated with a standardized HCl perhaps, okay, or any primary standard to ensure the concentration was in fact 0.104 molar. Okay, now if we were to prepare sodium hydroxide from scratch, okay, by calculation and then immediately assume the final concentration is going to be this, it's not going to be this. Okay, because in the process of preparing the sodium hydroxide solution, there's a very high chance that the sodium hydroxide might have absorbed moisture from air and you might have weighed lesser sodium hydroxide than you have to. Okay, there might be some water weight involved. So what's going to happen? You're going to end up with a diluted sodium hydroxide. Now, if you have a diluted sodium hydroxide, what's going to happen? You're going to end up using more solution or more titer to neutralize the lactic acid. Because, like I said, the sodium hydroxide is diluted, meaning the number of moles inside will not be sufficient, will not be equivalent to this concentration, because the final concentration would not be this, it will be lower. So more solution or more sodium hydroxide will be needed to neutralize lactic acid. So what's going to happen? You're going to end up with higher titer values. And what type of error it is? Now, as long as you use this solution, you're always going to end up with a higher titer value. Your titer value will not fluctuate higher or lower. It's always going to be higher. Now, if it's going to be always higher, your reading is systematic, or your reading is going to be precise but not accurate. So it is systematic error. And that's it for question number 38.